outside force stops it or acts upon it, right? Does anybody ever remember any other law?
For every action, there's a reaction.
There you
But
go.
it's
So for
right
every
there.
action, there's a reaction, right? That's Newton's third law. And believe it or not, right, this is when our musicians were actually scientifically literate, and they would actually use music like it was originally, one of its purposes is to actually inform, right, their listeners or their fans. So the musicians back in the days, right, music was a tool of teaching and educating, your fans or, next generation. So they used to put music, believe it or not, they used to put like science and science laws into music, right? So Bob Marley, right? For every action, you ever remember that song? There is that's Mr. Law of Motion. Again, this is, back then when musicians, well, a lot more of them took some type of, how can I put it? Ownership and say, you know what? Since I have this platform, I'm going to educate people. All right, guys, without further ado, right? So we're going to move on, right? So our essential question today is how do we describe Newton's laws of motion, right? And we know there's three, right? Anybody want to come up with a fourth one? No? No? All right, forget about it. All right, guys, so while most people know what Newton's law says, believe it or not, many people do not know what they mean or simply do not believe what they mean, right? So sometimes in science, there's this question sometimes where people will say, I don't believe it, right? Our president said that he doesn't believe the coronavirus, it was a hoax until he had it. Then all of a sudden, it's a fact, right? So believe it or not, right, that's one of the issues that we have in science, but science is completely objective, right? So you believe in something or not believing it, it doesn't mean that it will not impact you, right? So here are three laws. We're writing them down, the first, second, and third. And then I'm actually going to move my laptop so you guys could see. I actually have Newton's three laws in my classroom. I don't know if you guys can see. You guys see Newton's three laws right there? Am I talking to myself? Hello?
Yes, Miss Mars.
You guys
Yes.
see it? You're the only one that responded to me? Totally
Yes.
do. Yeah, so my three laws right there, that's my guys, right? So Newton and Einstein. So we're writing down the three laws, right? So you are expected to know the three laws. When we start doing force in the next unit, your job is to figure out which law applies to what example or which question. So that's going to be one of the skills. Can I figure out which law applies to the situation? So again, guys, remember that physics, we're using a lot of inference, right? So inference means that I have to know the concept and then I have to relate it to a real world application, right? So if you don't know the concept or you can't distinguish between which one, it's going to be harder, right? So that's going to be like one of the big skills here is to know which law is applied to which situation or which problem set. So I'm going to be quiet and have you guys copy this down, right? For number one, make sure that you underline the word unbalanced force, right? So Newton's three laws, believe it or not, it has to do with forces that are balanced and when forces are not balanced. You learn it? You learn it? I need more coffee. Are you guys done?
No.
No, not yet? Okay. And then we, like I'm gonna break down these laws and give you like the key takeaway, right? For each of these different laws. And then we're gonna look at real world application to some of these laws, especially in the world of sports, right? And automobiles, right? Definitely Newton's first, second, and third law is applied, right? When you have collision, we're gonna talk about specifically football. I'm not gonna go into CTE, right? But it's related to Newton's first, second, and third law. Okay, ladies and gentlemen, can I start? Can I move on or no?
Yes.
Okay. So
Yeah.
the first law again, right, says an object at rest will stay at rest, and an object in motion will stay in motion, right, at constant velocity. So if the velocity is constant, what can you tell me about the acceleration? What would the acceleration be if the velocity is constant? We did this before, guys, last week. Hint. Hello?
Hold on, Miss Morris. I'm not done copying.
Okay, so somebody else could pitch in while people are still copying. If the velocity is constant, what can you tell me about the acceleration? The acceleration therefore will be what then?
Also constant.
Constant? Okay, anybody else? What is it? What is the formula for acceleration? All right, guys. If I keep asking questions and nobody is responding, I'm just gonna stop and I'll just give you the
There,
assignment and actively learn.
there will be zero acceleration.
Yeah. Yes, so the acceleration will be zero, right? Because velocity, right? Acceleration is the delta V over delta T. So delta V, if there's no change, it's going to be like 12 minus 12. 12 minus 12 is zero, right? Zero divided by any number is going to be zero. You understand math, right? So if the velocity is zero, I'm sorry, the velocity is constant, right? The acceleration is going to be zero, right? Unless acted on an unbalanced force. So for the first law, right? The first law only applies to unbalanced forces, right? So I want you to, like I said, highlight or underline unbalanced force. Now, Newton's second law, it says force equals mass times acceleration, right? So what do you guys think? Mass times acceleration. Think about that. Is this a balanced or an unbalanced force?
Balance?
This one is actually going to be an unbalanced force, right? But sometimes, right, if the acceleration is zero in this case, right, zero times any mass would be zero. Does that make sense? So if the acceleration again is zero, second law, the force will be zero, right? But now when we get later on, right, next week when I start teaching forces, sometimes when the force is zero doesn't mean that there is no force applied, because when we get into Newton's third law, especially, right, we could talk about that, right? So a car sitting in a parking spot, does that mean that the car is not moving? But does that mean that there is no force acting on the car? So that's a whole nother story. Does that make sense, guys? And Newton's third law, right, it says for every action there's an equal and opposite reaction, right? Okay, so the first law, right, again, the only thing that I want you to write that you already have for the first law is that it's also known as the law of inertia, right? So what I have here is the same thing that you have on the for the first law. So the only thing you're gonna write is the law of inertia. So they're gonna ask you which one of Newton's law is known as the law of inertia, right? And it's the first law. Everybody's good? Can I change it? So again, you're not writing anything else because you already have the definition, right?
Yeah, you could change it.
Okay. Now, for the first law, right? I'm gonna have you guys write this, and then I'll explain. Oh crap! Hold on 1 second. This is too big. Hold on, you can't see all the words. Un momento, por favor. Okay. Nope. Sorry, I'm trying to change the font so you can see all the words. Okay. Better?
It was fine before, but I mean, yeah.
No, some of the words was behind the picture of the pumpkin. And see, it's perfect because, guess what? Look at the nice fall colors, right? See, I'm in the season.
Okay.
And I know this year that New York State and the mayor, right, there's no quote unquote Halloween, right? But we're in a pandemic, which is scary. So our Halloween will be the pandemic. That alone is scary, right? But I'm trying to stay in the season. in the festivities, right? So what I have in bold in another color, in the blue, it says inertia is the tendency of an object to resist changes in its velocity. So I need you guys to underline those words, right? So they're gonna give you an example and they're gonna ask you which object has the greatest inertia. And I'm gonna explain to you guys, what determines the greatest or the least inertia. So think about it, right? If an object wants to resist a change in velocity, you guys remember what the definition of velocity is? Hello? What's the definition of velocity, or what is velocity basically?
An object's the position object changes or something.
Okay, so the position and something else, right? So it has to have direction because it's a vector, and what else? So the questions that we did last week, right? What word did they
It's the
use?
speed of
Speed.
that
So
certain
velocity
direction.
is like the speed with a direction, right? So almost like the GPS, right? If the GPS gives me no direction, believe me, I will end up in somebody's backyard or I will end up in an accident, right? So if it says just go 100 meters, right, and then go 500, right? If they don't tell me north, west, south, right, make a right here, make a left, make a U-turn, I'm going to end up in the wrong place. Does that make sense, guys? Right? So it says an inertia is a tendency of an object to resist changes, right? So in other words, if I'm trying to change the direction of a vehicle, so let's say a car, right, is going north, right, in that direction. What is the biggest, or what is the number one, how can I put it? The number one variable that is going to be able to resist a change in velocity, right? So that's what we're going to talk about later on, right? So the example here says these pumpkins will not move unless acted by an unbalanced force, right? So I don't know, maybe the table will come crashing down, right, from the weight of the pumpkin, and then the pumpkins will move. Or maybe somebody will come and pick up the pumpkin again, right? It's an unbalanced force. Everybody understand that, guys? Yes? Okay,
Yeah.
let's keep teaching, right? So this is just another example of Newton's first law, right? So this is for golfing. I know you guys probably don't like golfing, right? So it says once airborne, unless acted upon by an unbalanced force, gravity, in this case, and fluid friction, right? It would never stop. So this ball is going to keep going unless gravity or some type of friction. In this case, it might be the wind, right? It might be the snow. It might be, the dirt, right? From the, when you hit the ball, right? The dirt, the grass, something else is going to stop it. Does that make sense, guys? Or maybe like an animal, maybe like a chipmunk or something happen to be around, right? Or a tree. Something has to stop it unless it's going to keep going. Everybody understand this one?
Yeah.
Okay, can I change it? Not yet?
No.
No.
All right, at least I'm asking. I'm getting excited. I like Newton. My students in the class think I'm crazy, guys.
Because you are crazy.
Oh, well, thank you. Thanks. I can change it, guys?
Yeah.
Okay. All right, guys. So again, right, this is just an example again of Newton's first law, right? So the wind or the golfer is basically, right, what will stop, right? The ball will tee on forever, right? So this is the same example before, right? I'm gonna move on. Now it says, why then do we observe everyday objects in motion slowing down, right? So why is it that objects that we see every day slows down, right? So I don't know about you guys, right? I try to push the refrigerator, it's not moving. Or my bed, Or I try to push the TV, right? It depends how big it is. Well, nowadays the TVs are easy, right? So they're lighter. That's not a good example. I try to push my car, it doesn't move. What else? I try to push my son and he doesn't move. So why is it that objects, right, are slowing down or becoming motionless, right, without an outside force? So the whole idea here, right, it's a force that we sometimes cannot see, right? So there are some forces that are invisible to our naked eyes, right? So when we're doing forces, one of the biggest takeaway is that you have to think very carefully about the forces. Some of them is going to be obvious, and the other forces that are acting on the object, you have to probably think about it. Like, wait a minute, oh, that might be magnetism. Magnetism is a non-contact force, yes, because I could have a magnet over here, right? And this magnet could pull the car from over there, but the magnet doesn't have to touch the car to pull it. Does that make sense, guys? Hello?
Yes.
Ma'am.
Yes.
Okay. All right, are you guys finished with this slide? Can I move to the next one?
Oh, you supposed to copy that one?
It's just explaining that a force is something that sometimes is invisible, right? So the takeaway here is just basically saying that the forces sometimes are not obvious. So sometimes you have to think very carefully before you could, before you realize what force is acting upon it, okay? And the next unit that we're going to is going to be forces.
Okay, you could go ahead.
Okay, everybody's good? All right, guys. So it says objects on Earth, right? Unlike the frictionless space the moon travels through, are under influence of friction. So what we're saying is that objects on Earth, there is friction, right? So for example, right, a good example would be in the wintertime, right? Or when the weather is bad, like yesterday was raining, right? The reason why the car could stop, right, is because the tires have friction. If the tires had no friction, the car would just keep going, right? And then that person might end up in a car accident. Does that make sense, guys, right? The same thing in a motorcycle. The same is true for, a bicycle, right? If there is no brakes, right? And if you hit the brakes, right? And the tires have no grip. If the tires are smooth, forget it. You're just going to keep on sliding forever. Does that make sense, guys, right? So we're saying here, right? On Earth, there is something called a frictional force, right? So if you look on your reference table, right, you will see like FF, which is frictional force, is equal to mu F of N, right? We're going to get into those formulas and topics, like I said, maybe like next week or the next 2 weeks, right? Come on, turn around. You're making me nervous. All right, guys, can I change this? Yes or no?
Yeah.
Okay. All right, guys. So these are just examples of frictional forces. The last one, I'm going to change it so you can see the font. My apologies. I don't know what I was thinking. Okay. All right, so you're just going to write down examples of the different type of frictional forces, right? Because in some of the questions, they're going to ask you to identify the frictional force acting on that object, right? They're going to ask you that sometimes. So these are the major types of frictional forces, right? I don't know. It depends on what people want to go into. I know that some people want to go into medicine, right? Believe it or not, there is a course in medical school called Physics of the Human Body. So especially for people that want to go into like, certain specialty, like, what do you call it? I can't think straight. Let's say orthodontist, right? Where you have to straighten the teeth, right? That's all physics. Go into Oh man, I can't think straight. Oh gosh, I can't think straight. The bone specialist. I don't remember what it's called, right? That,
Chiropractor.
not the chiropractor, the other one. I can't think straight. It starts with an O.
What was the question?
The bone specialist.
Orthopedic.
Yeah, there you go. That one. Yeah, there you go. I need help, right? So the orthopedic surgeon, right? There's a lot of physics. If the person is getting surgery, and believe it or not, I don't know if you guys watch those real ER stories. The doctor literally thinks about how the person's hand is supposed to work, right? So if they're doing hand surgery, right? And I've learned this, that a hand specialist is very rare because one, the hand does not have a lot, it has a lot of bones and a lot of tendons and and all these connections, right? And believe it or not, there's that much leeway for them to make a mistake. So if they make a mistake, right, believe it or not, the person probably will not be able to use that entire hand properly, right, for the rest of their life. So when the plastic surgeon shows up, right, there are other specialists, and their job is to make sure that, listen, even after the cosmetic, you want to make sure that that body part functions the way it's supposed to work, and that is all physics. So there's a class called Physics of the Human Body. One of my former students in medical school, that was her first class that she took in medical school, right? So, if you're into, if you want to go into mechanics, right? If you want to go into, specialize in mechanics, right? To fix cars, that's all about physics, how the car runs, right? If you want to become a pilot, that's all physics, right? All right, guys. So it says there are four main types of friction. There's sliding friction, right? An example of that is the ice skater, right? So the skate is sliding on the ice, right? Or the hockey player, right? Same thing, if you're roller skating, the skate is rolling, right, on the surface, right? So that's sliding friction. Rolling friction would be like bowling, right? When you bowl, right? When the bowling ball is going down the alley, right? It's rolling. So that's an example of rolling friction. Fluid friction is a little bit more technical because fluid determines on the temperature. You guys remember that the higher the temperature, right? The molecules behave differently, right? And also think about the different states of matter, right? If the temperature changes drastically, the molecules will change from, let's say, gas to like the liquid form, right? So which is what happened like on the mountains, right? So in the mountains, right, what happened is because it's cooler, some of those molecules now become a solid. And that's why, like, let's say in Kilimanjaro, right? In the summer in Africa, it would be completely hot, right, on the surface. However, on top of the mountains, those same molecules now will crystallize and become like snow. Does that make sense, guys? So the reason why I say fluid, air, and liquid is because the molecules in air, depending on the temperature, could change states of matter. So they could go from gas to liquid, or they could go from liquid to solid, or they could go from gas directly to solid, right? It all depends on the temperature, and it's going to behave differently, right? One of the lessons we're going to talk about is the speed of sound and how that varies, right? So let's say that, I don't know, you're in the US Air Force, right? And you're flying one of those fighter jets, right? Those jets behave differently as you go to different, can I put it, altitudes, right? Because the air, if it's warmer to cooler, right? The sonic boom that is projected, sometimes it slows down, sometimes it actually, accelerates. It all depends on the temperature of the air around it, right? So that's what we're saying here, right? So an example of that would be air or water resistance. Static friction now, right, is initial friction and moving an object. So I don't know if you guys ever had the experience where you touch like a door or something, you get like a little static shock, right? If you comb your hair, right, aggressively, and you notice that if you look in the comb, sometimes the hair will stick to the comb, or if you brush it, right? But you have to be dry, right? Because friction, again, is a force that opposes motion, right? So if I put a lot of conditioner in my hair, right, and I comb it, there's not going to be any static because the conditioner is the opposite of friction, right? Everybody's good? No?
Yes.
Yeah.
Guys.
Yeah, I was gonna ask you something, but I
Go
don't
ahead,
know how to
Mama.
put the question.
Go ahead.
I don't know how to put the question.
Okay, just say the way it comes off to you.
Like, so when you go to the orthodontist, right?
Uh-huh.
Does that have anything to do with friction, like at all?
So the orthodontist, like when they put the braces on your teeth, right? They also want to make sure that how can I put it? That the braces, when you close your mouth, right? that the braces does not pull on, you know, the inside flesh, like inside your lip. Does that make sense? Because then you're gonna have those rips. When they're putting on, they wanna make sure that it fits in the space. So everything, you know what I'm trying to say, right? And then as the teeth is moving, right, and being corrected, again, that it fits your whole face, right? So the whole idea of ortho in physics and chemistry just means, it means a mirror image, right? So what they're trying to basically do is to make sure that everything is aligned, right, and equal and opposite on both sides. That's basically what they're doing, which is Newton's third law,
Okay.
right? So that's the whole process of how, you know, they make, like, you know, different tweaks. So you go, like, you know, every 6 weeks, and they're trying to change. Go ahead, baby. And they're trying to change, you know, just to make sure that is, you know, that is going in the right direction. Because, you know, imagine orthodontist, right, is making these changes and tweaks, and instead of your teeth getting straighter, it does the opposite, right? Then that will totally oppose, right, Newton's third law. Like, wait a minute, you're supposed to be going this way and you're going the opposite way, right? That don't make no sense, right? So an example of sliding friction, right, is if you slide a book across a table, right? You watch a slide to a rest position, right? It says a book comes to a rest, right, because of the presence of a force. Well, the force, again, is not obvious, right? The force being the force of friction. So there is a friction based on the material of the table that I'm actually sliding it, right? So if it's the table that I have inside of the classroom, right? Because it's made from a different material, the book is gonna slide more, right? If I have a wooden table, again, depends if the table is polished. If it's polished, it's gonna slide more. If the table has, you know, a tablecloth, it might not slide as much. Does that make sense, guys, right? So we get into friction, we're gonna talk about, if you look on the reference table, right? There's some frictional materials, right? The Muse, hold on 1 second. If you have a reference tables, guys, right? I want you to actually go there so you can see what I'm talking about. So there's different coefficient of frictions that are given to you on your reference table. Right, so this would be on page, 1 second, right? So if you go on page 1, right? You guys see the different coefficient of frictions? So that is based on the chemical properties of the compound that is, you know, that object is made from. So if it was wood versus wool versus silk, right? Versus asphalt, right? Versus, let's say, a dirt road, right? So a bike riding on a dirt road is going to behave differently than if you're riding that bike on an asphalt, right? That is paved, right? The same is true if you are sliding down the grass, right? Versus if I slide down in rocks, right? So the frictional force or the coefficient of friction is different. Everybody understand what I'm saying or no? Yes, no, Miss Morris, go away. So if you push in a table, right, in the room and there's carpet, the friction is going to be greater than if I push it and it's just a wooden floor. It's going to move easier. Does that make sense, guys? All right, guys, so we're going to go to the next one, right? So again, this is just Newton's first law, right? It says in the absence of a force, the book would continue to move at the same speed and direction forever, right? But why does it stop? Because there's friction that acts upon the object. So eventually the object has to come to rest, right? So that's basically the takeaway. Right, so the book is going to keep sliding until there's an outside force to stop it. Maybe somebody's hand, right? So if you want to think about a car, right? Let's say the car can't stop, right? For whatever reason. Something is going to stop that car. It might be a truck, it might be a bus, it might be a wall, it might be somebody's house, right? Something is going to stop the car, right? So when you have like machines or devices, right, that are out of control, if you can't stop it or the brakes doesn't work, nature is going to stop it. It's just not going to be nice.
Correct.
Everybody's good at this example.
Plus
I could change it.
3y plus z.
Yes.
Yeah.
Okay. All right, guys. So again, this is Newton's first law again, right? And this is explaining why you should wear your seatbelts. Right. So it says because of inertia, right? Objects, including you, is going to resist the motion. So notice that the car was going forward, right? Into the wall. What happened when the car stopped? The person continued to go forward. Does that make sense? Everybody see that? So that's why the person, you know, fell out the car. right? So that's the reason sometimes, you know, let's say that somebody's sitting in a car and they're not wearing a seatbelt, right? If your body is going to continue with the same velocity. So that means that the person now, right, if the car stops suddenly, that person now, if they don't have their seatbelt, is going to be, they're going to actually be thrown out of the, what do you call it, through the windshield, right? And those accidents is, you know, sometimes is deadly. Everybody's good? So that's an example of Newton's first law, or the law of inertia, applied in a bad way. Questions, anybody?
Nope.
Everybody's good, right? So another example of this, let's say the person is going straight and all of a sudden they turn right, right? What happened to the person's body? Even though the car all of a sudden changes direction, right? Your body is still going to be going the same direction. And that's why, you know, everybody all of a sudden they push forward, right? So that's what happened. All right, guys, so this is just, again, Newton's law of inertia, right? You don't have to write this one. The only thing I want you to write here, you see where it says right here, objects with the greater mass has the more inertia. That's what I want you to write. So the key takeaway here, right, for inertia, the greater the mass, the greater the inertia. And I'll explain what that means. And I think I'll probably stop after the first law because that's so much fun in Newton's first law. All right, so the more massive the object, the greater the inertia. Right, so think of a train and a car. Which one is more massive, the train or the car?
The train.
The train. So the train would have more inertia. What they're saying that, right? That the train is going north, right, at a certain force. Even if the train sees the person, let's say, I don't know, 2 blocks away, right, and the train tries to stop, they're not going to be able to stop, right? So they're actually going to they're going to hit that person, right? So because the train is so massive, right, it takes a lot more energy, and I have to stop at a larger distance for me to avoid hitting that, right? So which is why, right, the car should avoid the train because the train can't stop. They can't change the direction that easily, right? So it's easy for the car because the car weighs what, 3,000 pounds, I think, right? Unless you have, you know, the presidential limo, right, that has custom fitted fiberglass and all these other mechanisms, right, for safety, right? Those cars are heavier, but unless you know, you have a regular car, it's usually 3,000 to 3,500 pounds, right? Sorry, kilograms, right? Again, so the car is easier to turn. So in other words, the car, the driver, if they see the train coming, they could just turn real quick, right? The train now, if the train tries to turn, right, what's going to happen is that the train is going to derail. And then you're going to have a bigger problem. Does that make sense, guys?
Yeah.
Yes, does that make sense, guys? Everybody's good? So that's what we're saying, right? So again, think about